All right. So welcome to the course. This is going to be your first training video. We're going to be recording this, and you'll be able to go through it in the future as we'll be sharing it with you. So let me open up the syllabus first, and then I'll show you my slides and stuff, just so that you get a quick feel for where we are. So I'll be sharing my screen. Okay, so basically, this is the week one. We'd be covering some very introductory overviews of what are the kinds of paradigms in machine learning, just so that you have a bigger picture of what's in there. We're not going to delve into anything deeply. And then we're going to move into something that's kind of a prerequisite, really, for any material of this kind. So we're going to just refresh. It's like a primer on some basic probability and statistics concepts that are kind of relevant to get started on the techniques and the methods. So I know that we are not here just for doing a primer. So obviously we put in a very naive, a basic classification machine learning technique. It's called naive Bayes. It's very popular though. And it has its foundations very strongly in the basics of probability and statistics that we'll be covering. It really is an extension of the basic laws and rules of probability. And then linear regression elastic nets, there is a slight modification. I would be putting this in week 2 because week 2 is literally covering the problem of regression. We will cover what this problem is and how in what paradigm this falls and all that, but it seemed to us that it would be a more perfect fit in week 2, so that thing would be going here. But we'll be spending a more time in this in view of that change. So these are some updates that I wanted to share. This is not part of today's video. So basically, these are some goals we'll be setting for ourselves. I will be suggesting and sharing some links with you where you can find a lot of real-life data sets. And it might be useful for you to just go over it after the call at your own pace and try to identify at least 3 data sets that catch your eye or you would feel interested to analyze more and use as a possible data set for your first project. So I'll be guiding you through the project as well, but we need a data set hands-on for you to work on. So that's a very soft goal in here. So it's not like an assignment, but it's highly recommended that you try to find a data set over the coming week. All right, so let me share my material. Feel free to stop me at any point, and it's highly encouraged. Feel free and informal. That's the overall guideline here. All right, so let's just do a very quick 1 or like 3-4 slide overview of the bigger picture. So we're just looking at bigger buckets in here before we go into more technicalities, right? So what is machine learning? You basically are looking at a set of observations, but it's good to get in the beginning of your learning process some of the terminologies that are used often correctly, right? So people can call them observations. People also call them samples. So a set of samples. That's your input data, and then you want to uncover something about the underlying process that is generating that data, so that you can basically answer questions from a data investigation perspective, right? This is a very overall goal. This is something that I'm sure data science as a word itself speaks for itself, right? So there's a very broad premise. So machine learning, so there's not like all machine learning techniques solve the same kind of a problem. There are different kinds of machine learning techniques and different kinds of paradigms within machine learning itself. That's the overall point. So I listed some of them here. I will do a 1 or 2 liner about what kind of a paradigm this is and what kind of problems fall within this paradigm. This is a very high level view. All right, that's the goal. And then we would be starting with our focus during the coming weeks and also a bit in this week towards the end of the course when we focus on the naive Bayes technique on the paradigm of supervised learning. That's why I put it first. There's a bunch of problems in supervised learning that are very popular. And this is something every data scientist should be learning to start with. And then once you get your view good on this, then you can jump into these other paradigms. So what is supervised learning? So in machine learning, you again have a set of observations, but in supervised learning, there's going to be observations and what is known as a response variable or a label. So you have a set of input variables, which can be coming from your database or whatever your business setup is or your academic setup is. So that's your input variables. Those are your observations. But each observation comes with a label or also a response variable. So label and response are, again, very popular terminologies. So it's good to set that straight. Now, what is a label or a response? So observations are just input variables. Now, label or response is, so let's go one at a time. So a label is basically a category that the observation that you're observing falls under. So let me give an example. So if you're looking at observations, which are basically emails, right? So Gmail looks at a lot of emails as its observations. And a label that is tagged to each email or each observation is basically, for example, whether the email is spam or not spam, right? So that's a very popular classification problem. Gmail does not do this manually. They have a machine learning classification model that automatically looks at its observations and tries to classify into one of these labels that are possible, whether it's spam or no spam. And it also gets feedback from its users, right? Because people, when they receive a spam email, most likely they send it to the spam folder. So that also reinforces the model that Gmail is training and using. So that's the supervised setup. You have input. You also have an output variable. The output variable is a label, if it's a categorical or like a class variable that you're classifying. But if it's a regression problem, which is another popular supervised learning, then it's just a real valued number. It's just a number. It's not a category anymore. So if you're trying to look at data about real estate, right? So for any given latitude, longitude in the world, if you're looking at data about real estate, right? That any data that would help guide you towards determining what is the price that a house would sell at for any given size at that particular lat long. If that's the question you want to answer. So your output is you want to figure out what is the price that is optimal, is a max price that you can sell your house at if you were having it in that particular location. Now, what are the input observations you could use? You could use the demographic information, the socioeconomics, right? Are people reasonably well off, or is it very poverty stricken, right? You can look at how many members are in each household. You can look at how their education levels are. You can look at how the crime is. All this is input data. So these are the observations. But your output is a response variable, which is a real valued number that you're trying to predict, which is the house value, right? At what price you should be selling it. So this is the supervised learning setting at a very high level. You have input, you have output. Unsupervised, you only have input variables. There's nothing given to you as a target that your model should learn. No target, no output, no response, no label variable specifically labeled as an output variable. All you have is input variables. So it's like data exploration, right? What can you do with your models to explore the data and come up about and reason about the observation. So you're trying to label it automatically in a way and say, hey, if you give me 1,000 rows of data with, say, 100 variables, if my unsupervised model is going to say things like, hey, maybe these particular subset of 100 rows out of the 1,000 belong to one particular cluster because they're behaving similarly. And now I'm looking at just these 100 variables and trying to figure out why they're a part of a cluster. Maybe because they're sharing a lot of attributes that are similar to each other. So that's an unsupervised learning problem. So you're gradually coming up with your learnings of your within your data set without having a target in mind beforehand. That's the overall techniques that fall in unsupervised learning. Then there is reinforcement learning. This is very interesting in a way that a lot of video games use reinforcement learning. So basically, here the concept is you get feedback and you take action. So you're in a situation where you're using your model where any decision that the model takes is going to have an output, obviously, but the output is like a reward or like a punishment or like a cost. So based on your explorations of your model, you'll be getting different rewards and costs that you will gain and you will bear. And based on that, you need to make your next decision. Again, you get some reward or you bear some cost, and based on that, you take your third decision. And the goal is you want to obviously maximize your reward and minimize your cost or punishment, right? So this is the concept of reinforcement learning, where there's this sequential decision making that you're making. So you're taking decisions in sequence, and you're also getting rewards in sequence, and you want to update your learning mechanism based on that. All right, so semi-supervised learning, again, at a very high level, it's kind of a mix of supervised and unsupervised. That's why it's very aptly named. So here the situation is, you have, again, a bunch of observations, variables or response variables, your output variable. But the caveat that makes the difference between supervised and semi-supervised is this. Not all your observations are labeled. So if you had 1,000 rows of data, rows have labels and 300 do not. Or maybe only 50 rows have labels. So you only know which 50 emails are spam or not spam. You don't know which of the other 950 emails, what they are. And you want to use the best of supervised and unsupervised worlds, right? You have labels for some, you don't have labels for a lot. So you want to use a semi-supervised setting. This is kind of very useful in industrial settings or in real life or in research settings because sometimes the process of labeling is costly. A company like Gmail, maybe there are so many users and there's a big user base and they're able to get their spam, no spam labels a lot easier. But in some situations, like say in biology or in genetics, there is something called microarray data analysis. Microarray is basically it's like a hardware kind of chip. People put in their blood samples and do some tests or that data about the genetic information about the person. So if you want to build models that will try to identify based on the genetic information of the person on whether he is likely to get cancer or not, or whether he's likely to get diabetes or not from a genetic perspective. The thing is, these tests are very costly, okay? So you cannot label beforehand. So sometimes what people do is they collect labels for maybe 100 people. So they have maybe and then they would have input data for 1,000 or 10,000 other people, but they would have proper labels only for 100 people who are cancer patients or not cancer patients, but the other, you do not know what they're headed towards. So in those settings, they use semi-supervised learning, for example. Active learning is, again, kind of a sequential setup in terms of labeling. So you have a set of observations. What you see everywhere, like in supervised, unsupervised, everywhere you have observations, except for in reinforcement, where it's a sequential decision-making, right? Here, your reward is observed based on the decision you make. You have a fixed state space of decisions you can make, and you need to choose some decision, and then you get some reward. It's like playing chess. At any given moment, there is a list of, maybe it could be a one page full of list, or maybe just 2 moves that you can make. You need to take a move, and every move will give you some reward or punishment. So that's a slight difference here. Again, in active learning, there is some sequential part again going on in terms of the labeling process. So you have a set of observations, well and good, just like in supervised learning or in unsupervised learning. But for the label, you do not have any labels to start with. All you can do is you can find whatever observation you want to have labeled and then send it to the oracle. Oracle is like the god, he's someone who can do the labeling. This person could be a manual person in your company, maybe in a manufacturing setup. Maybe he will label this as something, as a defective part or a good part, or it could be anything, right? But he's someone that is either manually labeling it, or it's a machine that will label it, or it's a poll people will conduct and then label based on what the experts converge on what that label should be, right? But there is a process to get the labeling, and you cannot send all your rows into that process. It's very costly to do that. So what you do is you pick whatever rows you want to have labeled, and that subset you send for labeling. And then you pay some cost. Then you get the labeling done, and you get it back. Now, ideally, if you have like $1 million with you, and if the labeling is costly, you would send, and if you're willing to waste money, you can send everything for labeling. Then it becomes a supervised problem. But that's not what you want to do. You want to minimize your cost of labeling, but still you want to have reasonable prediction accuracy. That's the active learning setting. Online learning, online, sometimes as the name suggests, is what it is. Here, your data is not coming in, not available in a batch, right? So you don't have a set of data given to you. Data is streaming data, and you cannot you cannot store data in an unlimited fashion, especially if it's streaming every few microseconds. And data is just coming in as a flow and going out, and you only have a limited amount of storage capacity. That limited amount still could be a big number or a small number, but this is the setup. You have streaming data. You want to have a model that takes care of the online streaming nature of the data and be able to do the prediction. Manifold learning, it is part of unsupervised learning. Unsupervised has a lot of other techniques, but this is gaining its popularity in itself, so people have put it aside. There are other terminologies people use to refer this, like embeddings and stuff. But here they assume that you have, again, data, but in unsupervised you do not have labels. So all they assume is in manifold learning that your data lies on some sort of a surface or some geometry. There is some geometry to the data. There is some shape to it. And people want to make use of that shape of the data to make their analysis about that data. learning is basically, it's almost like reinforcement learning, but it's not always about rewards or punishments. You interact, you observe something. That may be a good thing or bad thing. That's later, but you observe something. And based on that, you remember that this is what happened if I did this kind of a thing. And then you again keep going. So it's almost like reinforcement learning, but it's not only about rewards and punishments. So it's interactive. Any questions at this point? I know this is just a high-level overview just to make you feel comfortable about how many variations and what all is there in machine learning, for example. Okay, so let's jump in. Yeah, I hear something. Is there a question? Okay, so let's keep jumping and going forward into more technical details.
Pranit, one question, sorry. So you gave the example of email and spam, right? So can you give any other examples so that we can use like any of these techniques?
Yeah, so definitely. So for supervised, I gave the email spam, no spam. And then the prediction problem where you're predicting response variable, so the housing value prediction. Supervised learning would be like, I will give you a bunch of data about credit card transactions. I do not know which one is fraud and which one is not a fraudulent transaction. So you want to see if you can group the data into two groups where when you then delve into each group, you would see, oh, this group has all the kinds of right properties that it ends up being looking like very fraudulent. The other group doesn't look fraudulent. So that's unsupervised learning. Or if you're trying to detect some anomaly, basically. For example, you can treat this problem as a supervised problem as well. But the thing is, if you do not have labels, then it's unsupervised. Any supervised problem where you want to predict or classify, but you do not have the true answer, ground truth, then it's unsupervised. So these are kind of similar and easier to explain. Reinforcement learning is very useful when you're trying to game the system. So there's a system where you need to take actions and you get rewards and stuff, like I said. So a good real-life example would be if you're trying to come up with teaching your computer how to play chess. So that's a very reinforcement learning problem. There's a fixed, discrete amount of steps you can take, and you need to choose the right step, and then you have something. But in reinforcement learning, there's an added issue. It's not always a deterministic game that you're trying to learn, right? Chess is very deterministic, right? But sometimes your game might have noise in it, so there's some uncertainty involved, right? So you want to fight your way against that uncertainty to see how your learning influences the system. So a lot of people use reinforcement learning, for example, in industry, in advertising. So you have a bunch of different demographics of people that you can reach so that your ad is viewed by the most people or clicked by the most people, which is what you want to do as an advertiser. That's when your client will pay you. So say you're advertising a smartphone from a company, and they're going to pay you if you get them the most number of clicks. So you need to figure out a model that you reach the right number of people that will give you, and the right kind of people that give you the most clicks. So there's a decision you need to decide. If you had 10 buckets of people, say one bucket was people that eat chicken wings and eat pizza most of the time. There's another bucket of people who only eat Asian bucket of people who drive a Toyota Corolla. There's a bucket of people who drive only very high-end cars. There's a bucket of people who work very long hours on the Wall Street style companies in New York. There's a bucket of people who are students. So there's gender differences, right? So for any given smartphone product, you want to figure out how you game your decision making of which bucket to reach in what proportion through your advertising platform so that you get the most rewards. And every time you reach a bucket of people, you're spending money because you're spending money and time in reaching out to those people. And you then get a reward based on the decision you take. You get a reward of what your click-through rate is. Did a lot of people click the ads or very few people clicked your ads where you spent a lot of money in reaching out to them, but you didn't get any clicks out. So your client is not going to pay you much because you only reached 5 people and he wanted you to reach 5 million people that clicked the ads. So that's a very good example of reinforcement learning people use in industry. Semi-supervised, again, in industry use. So say, for example, in fraud detection, it's very hard to have 1,000 investigators calling everyone and verifying everyone's records to label any transaction or any behavior as fraudulent in a company. So they use, say, 100 investigators all over the world to get 24/7 coverage. And then 100 investigators, obviously they're humans, so they cannot label the millions of transactions a company or a banking company would be having, right? they label whatever they can. So you only have a partial labeling, and then the rest the model needs to figure out. You have input data about every transaction, but only partial labels that they're able to populate using these 100 investigators that you're paying. So you want to use that setup to build a fraud detection model. Active learning, similar setup. You're paying to send, say, a record to an investigator, and you're paying for his time and money. So you're going to only send those records that you think are very hard for a model to classify whether it is fraudulent or not. So you're going to figure out which records will give you the biggest hurdle or uncertainty beforehand in being able to classify whether it's fraudulent or not, and based on that you send it to the investigator. So it's a similar setup. Online learning, it's there everywhere. It's not as popular as supervised, but the setup you'll see in a lot of places, especially manufacturing environments. There is a manufacturing line, things are going in and out, and you're always collecting data, and then there's a time series of data that's flowing in and out. So you want to make sure that you respect the streaming nature of the data and the fact that you cannot store everything forever, because then you'll be building data centers every day or every month. Costs to store things forever and process it. So you want to take decisions in a streaming fashion. Very popular in manufacturing environments. Manifold learning, this is more of a technique. It's applied whenever unsupervised is, but it's getting popular separately. Interactive learning, if you're trying to build this is kind of more futuristic. If you have a very simple robot that you built that can take only 5 kinds of actions, and you want to build some model into its chips, into its hardware, so that based on your interactions with the robot, it's going to learn something from you. So a simple robot would be something that will memorize your actions, right? Whatever you're saying is going to repeat like a parrot or something, or there could be a little more better learning process where the interactions is trying to think and induce rules and connections. So that's the interactive learning setup. So I put it very much there. Yeah.
Okay, so in Netflix, when we watch movie and when we give the feedback, like I give 5 rating or 3 rating, something like that, they start suggesting me the movie. So if I watch horror movie, they start suggesting me the horror movie. So do they use reinforcement learning?
They could, but that's not what is used in general. So this is known as a recommendation system problem, or recommender system. So what they do is, it's more of supervised learning, but it's kind of incomplete data. So you can put it in supervised or semi-supervised settings. It's not necessarily reinforcement that you're doing there. You are getting ratings, and you possibly can reinforcement learning problem. But the thing is, your decisions, input space of decisions you can take, which is the kind of movies that you can offer them, is kind of very huge. So what they do is they look at it as a matrix of users and movies. We have a big chart of users versus movies and what rating the user gave for that movie, but no user can watch all movies on Netflix. So it's going to be a very highly incomplete matrix. So the problem is you want to figure out what those incomplete numbers are based on the completed values in that user versus movie rating matrix. Otherwise, some people also take an unsupervised because you're trying to predict based on this behavior with the other behavior would have been. It's treated more like a prediction problem.
Okay, thank you, Puneet.
Yeah, cool. So let's keep going ahead on the slides. So now a little more into the technical content, but still giving you an overview. So these are things that I'll skip quickly. So an example this is like a very cartoonish example, right? It's not very useful, but it's cartoonish. But it's useful to understand the problem. So say if you're looking at coins from vending machines, and obviously there are different kinds of coins that come out, right? So you want to if you want to just look at the properties of this coin, so the x-axis is size, y-axis is weight, and just based on size and weight of any coin, you want to build a model that will automatically classify whether it is the quarter, if it's 5 cents, if it's 1 cent, or 1 dime. So you plot your size versus weight data for a lot of coins. It's very clear separation between the patterns because you know the label beforehand that this group is belonging to quarter, this group is belonging to 5 cents. 1 cent group, this is the 1 dime group as colored, and this is the supervised setting. You have the input data of size and weight, which are your observations, and you have for each observation the label tagged already. It will tell you beforehand that these are coming from this kind of coin. So all your model needs to do is be able to classify this. So you need to be able to draw a line or some curve or some sort of a function that separates one from the other. So if you can do the separation, then in the future when the data falls on this side of the line or the curve or your separation, your learning model you will say, okay, it seems to be like quarter. If it falls somewhere in this range, if your model is good enough, then you would say 5 cents, that kind of thing. Then there will always be mistakes. You would make false decisions sometimes, like a 5 cents being labeled as a quarter. But the point is, nothing is like a crystal ball like in movies where the whole future is completely known to you, right? So the goal is to minimize your future error and maximize your prediction accuracy. It may not be 100%, it depends on what the problem is. If it's a very easy problem, maybe it is 100%. Unsupervised learning, same plot, size was a weight, but I'm not giving you which point is which coin. See, I didn't do any color in here. I didn't give you any information. All you can do is, maybe I will try to separate this into however number of groups it naturally separates into based on their similarity relation, proximity or distance relation between pairs of points. Then maybe if it's a good algorithm, I can separate these 4 into 4 different clusters, and then I will delve into each cluster and then see, okay, this seems like looking very much like a 5 cent coin versus a quarter or whatever it is, and that's unsupervised setup. Problem in unsupervised is you can put whatever technique. So it's like techniques, if they're a bad technique, it's like good data in, garbage out, right? Or if your data is bad, then even worse, garbage in, garbage out. But the thing is, you don't know the ground truth. And if you want to know the ground truth, you need to do more work. That is the setup you're in. They're not giving you the ground truth beforehand. So if you're a data scientist, if they only give you this, you need to figure out without knowing the ground truth whether you're doing good or not. So that's a hard problem. But people sometimes don't care. They just go by intuition. They separate into clusters and say, okay, this is what it is. They only maybe sample a few points from each cluster they got and see and check. They will not check every data point if you have a million rows that you cluster into 4 clusters. And then they'll say, okay, let's think this is what this is. There is some intuition involved, and it's hard to evaluate it scientifically in terms of your performance. Here, everything can be evaluated completely because you know the ground truth, you know what the model is saying, so you can match things and say how good your model is or not. Reinforcement learning, this is a cartoonish example, right? It is like a casino, a kind of a machine, slot machine. But say if it was a very intelligent machine, you need to make a decision on whether you put money on this cartoon or this cartoon or this cartoon, right? Based on how much money you put and what reward you're getting, you can keep changing your decision in order to maximize your reward. Never try this in a casino because the odds are very stacked against you. It's like very uniformly random. Okay, now we are getting into the probability and statistics primer. This is very important for you to understand the naive-Bayes technique, the first technique we're going to cover, which is a classification technique in the supervised paradigm of machine learning. Okay, so it's a supervised learning classification technique, naive-Bayes. But this is the probability and statistics. It's a good foundation to understand that technique. And not only that technique, your future classes in general, you would be kind of inclining your mindset towards this kind of a thinking. There is a reason sometimes people find primers and foundations to be boring, but it's very important. There's a reason it is boring because your mind is kind of fighting against learning these new topics. If you've already gone through these topics, well and good, it'll be easy on you. But the reason you want to go through it is because once you have a good foundation, or if your prerequisites are strong, in the future when you face advanced material and advanced technical material and advanced techniques, you wouldn't be like, oh my God, this is so many things on the board. I'm not even able to understand anything in here. You don't want to get there very soon. At some point, if you keep pushing yourself, you will find some technique. It's very hard to understand. But if your prerequisites are strong, you would go much longer, and you'd be able to learn things yourself gradually. So, all right. So probability. I mean, we all have technical backgrounds, so we know what a probability is. So it's some sort of a chance behavior, right? There's some unpredictability in there. There's some randomness. In the short run, so if you're looking at only a few samples, if I had a biased coin, if I gave you only 3 samples of tosses, and if it was like head, tail, you only have 3 chances to figure out what the true bias, what is the true proportion of heads and tails you would get if you had run it in the long run. So you would look at samples, which is your short run, but you want to make the right decision about the truth in the long run. If your decision-making model or intelligence is strong enough, then when you use it in the long run, it will give you the right answers. Okay, so the probability of any outcome of a random phenomena is so this is a basic formula, right? How do you measure probability? It's a proportion of a probability of any given outcome is a proportion of times that the particular outcome occurs out of a total number of samples that you've generated, right? So if you're looking at an unbiased coin, if you generate 1,000 samples, the proportion of heads and tails would start converging towards half and half, because you will count how many heads you got. Maybe if you did 1,000 trials and if you got 499 heads and 501 tails, it's almost half and half. It's kind of approximating towards the truth. Maybe if you did 10,000, there would be 0.5 each, the proportion of heads and tails you'd get. All right, so the sample space is a set of all possible outcomes. This is terminology. Event is any set of outcome of interest, right? So sample space is all possible results you could get at any given trial. And then event is a particular outcome that you're trying to measure the probability for. So that's why you're measuring the probability of one event at a time. So it's the number of times this, the relative frequency that just means the number of times this event is occurring and the total number of infinite trials that you're trying to do. So this is probability of A, right? This is the term, this is the notation. All right, so suppose you roll a die and take their sum, right? So you got these sums that you collected. Now the question is, what is the probability the sum is phi, right? You guys have done so much education yourself, so you'll be able to figure this out, right? You just look at how many ways a sum of 5 can happen. So like 2 plus 3, 3 plus 2, 4 plus 1, so on. So you count that and then you divide by the total number of possibilities. So let's keep moving. Let's go into more towards the machine learning aspect. If you have any questions at some point, you can ask me. So now we're looking at two events, right? So this is notation for both events occurring. So it's like an OR notation. So either A or B occurs is what you're trying to measure with this. It's what you're trying to denote with this notation. A intersection is like both occur at the same time. So it's like an AND kind of a notation. So this is the complement, right? So this is like, what is the probability that A does not occur is noted by complements. It's 1 minus the probability of A. Probability is always between 0 and 1. A and B are mutually exclusive if both cannot occur at the same time. All right. So if there is no possibility for these occurring at the same time, then you call it mutually exclusive. Then you can only observe A or B. You cannot observe A and B at the same time. So now if A and B are independent events, so independence is very important in understanding naive Bayes. So the idea of independent events is that the probability of two events occurring at the same time, if they are only influenced by their individual probabilities and are represented as a product, then it's an independent event. But if there is more to it, if you have other terms, then it's not an independent event. So basically, me maybe knocking on the door is independent of rain falling as soon as I knock on the door. So these are independent things. A is knocking on the door, B is rain falling. So that's an example of an independent event. Now there's some more mathematical intuition behind what's going on here on why you got that formula the way it is. So let me open that up. I know Venkat was also mentioning that I'm interested in formulas. So basically, we're going to cover in the next few slides a concept of distribution function, which is basically a function that's denoted by f, which takes in a value that you're measuring for your event. So if x is what you're measuring, and if it takes a value of whatever you think it should be taking, and you want to measure the probability of x taking a value of phi. So this could be the sum of the two die, for example. Now x could have been anything else. It's a function of x that can take different numbers. And its output is going to be a probability. It will give you an answer between 0 and 1, one number between 0 and 1. Right? So this is a probability distribution function. This is known as a probability density function. F, that's the name of this function. So it's basically a function that takes what events you're trying to measure, and it will give you the probability of it. So if you plotted this function, you can do this measurement of this function for just one random variable. Then it's a PDF it's a univariate PDF. You can measure the random variable, the probability density function, if it's like a joint probability of x comma y. So if I was asking, what is the probability of x taking a number phi and y taking a number 3? So two at the same time, right? So you're measuring this and this. Then the thing is, I will give you a very lengthy formula of this in terms of integrals and calculus. In terms of how you can measure these phenomena, what happens is your probability density function, when you write down the formula and you look at the derivation, it literally splits down into the probability density function of x times probability density function of y, only if f and y.
Remy?
Yes.
One quick question here.
Yes.
In general, There are the three things I'm hearing a lot, like algebra, calculus, probability. These are the major three underlying base concepts. So what is the difference between a differentiation versus integral? Because overall the spectrum, all this machine learning, driven by a mathematical formulas. So for instance, okay, d of x by dx equal to 1, or integral of -1 to 0 1 d by dx of x square, something. These all are for some reason they derived and classifying certain things, right? So just I'm trying to correlate in which scenario what is the differentiation is deriving and what is integral is deriving and
Sure.
what is our sine, cosine, tan, what that is. Because I learned everything when my education, in my school period, just like by hearted. Tan 45, 1, cos 60, 2, like we by hearted, but we don't know what is those.
Sure, yeah, you're asking for basically, so we're going through a probability primer right now, but yeah, we can always do a calculus primer at some point where we cover these concepts, but I can answer super quick. But we're going to do a more detailed primer at some point for linear algebra, calculus separately. This is going to help your learning of other techniques in the future. But so not to deviate, but still to answer your question, if you're plotting a function, right? This is x is your x-axis, and you're plotting some function f of x on the y-axis. So this is just a standard 2D plot of a univariate function. And if the plot looks like this, the rate of change in here is slower between the first value of x and the second value of x. As your x increases a little bit, the rate of change is much lower. But here, with slight increase in x, your rate of change in what you're observing, f of x, is much higher. Your derivative is measuring this rate of change at any given point. That's your first derivative. So that is df of x by d of x. That's the notation. Now, if you're looking at the second derivative, what you're looking at is the rate of change as you keep increasing x at any given point a little bit and measure how much the rate of change is, which is you measure your derivatives in an Excel sheet. And then if you want to look at what is the rate of change of those derivatives itself. So it basically tells you if at any given point you are at an increasing rate of change or at an decreasing rate of change. So you could have had a function like this as well, right? So your increasing rate of change is here. Here your second derivative is much higher. It's increasing much faster. But derivative is only at one given point. But the second derivative is looking at how the rate of change is varying at this given point versus this given point, right? So it's much faster. Here it's kind of increasing gradually. Here your second derivative is measuring is kind of increasing slowly. Same way around. Here it's the decreasing behavior. So at this point, your first derivative is 0 because there is no rate of change at that particular point. But your second derivative is negative because it knows that your first derivative is gradually reducing as you keep going towards the right side of the curve. It's just measuring how the rate of change of any given phenomena is. But we can do this. I think this is like a tangent, but this is what the derivative, this is truly the definition of derivative and second derivative. So we will.
So this is kind of differentiation. So integrals is similar.
Integral is basically well, you study together, but this is the concept of integral. So if you had, say, this curve you're looking at, you want to measure, or like this curve, the increasing curve. If you want to measure the area under this curve in intervals, so then you do an integration. Integral is a formula for computing, is a procedure for computing the area under this curve, under any function, right? Under this curve or any function between any two intervals.
Oh, okay.
So especially in terms of the probability density function, there is a very popular density function called normal distribution. So say if I'm plotting the probability of heights of students in a class, right? So if the average height, so in maybe 10th class, maybe the average height was 5'5", okay? Somewhere in here. So the probability of the average height is much higher because you're seeing a lot of students around the 5'5" height. But there's a very few students which have a height less than 5 feet or height more than 6 feet. So these are the tails. So here the probability is lower because your y-axis is your probability density function, this function. X-axis is the events that your data can take. So if the height was equal to 5'5", the probability is high, maybe 0.7. If the height is 4'1" or 7'2" or 6'5" in 10th class, in 10th grade, then the probabilities are lower. So that's probability density function. Now, there is a theorem that the sum of all the probabilities under this function. So the sum of probabilities, since this is a continuous function, you cannot measure everything at every small increment, right? You cannot measure the sum at 4 feet, 4.001, 4.002, and so on till 6 feet or whatever, infinity, right? So the summation of all these probabilities is what is given by integral. And that summation is exactly the same as the area under this curve. So that is the integral of the density function. That will give you the sum of probabilities within any given interval. So you can ask the sum of probabilities all through, then it's going to be 1. Any density function has a sum of probability of 1. But if you want to know the sum of probabilities, or what is the probability of students having a height 5'1" and height 5'7". So you only are interested in the probability of a height being above 5'1" and less than or equal to 5'7". So then what you do, you take the probability at 5'1", and then so on, you keep on increasing it till 5'7". So you cannot do this manually for a continuous curve. So you compute the integral of the density functions. You only compute the area between these two intervals. So whatever that number is, so if the number, it'll always be less than or equal to 1. If this number is 0.7, then you will say there is a probability of 0.7 for observing a student's height between 5'1" and 5'7". So that relation with
yeah, thank you. It helps a lot.
Cool. Yeah, good. So great. So let's keep going on a couple other concepts. We covered all this. So if you had independent events, like I said, if you had two events that are independent, then the probability of A and B occurring is going to be the product of their probabilities. These are probability laws. There are theorems that prove why the formula is the way it is. All right, but this is a rule that's worth remembering as well, apart from understanding how the formula's derivation works. So if you had more events and if they're independent, so they're not depending on each other. Literally, dependence can be used as a word in real life English, right? So me eating bread for my breakfast has nothing to do with India winning the cricket match tomorrow. These are independent events. These are two different events, but they're independent, right? So the probability of me eating breakfast for bread may be low. I don't like to eat bread for breakfast. So if my probability of eating bread for breakfast is 0.2, and if the probability of India defeating Zimbabwe or some country is 0.9, the joint probability is just the product of these probabilities. It's not going to be any other function. So these are independent events. All right. Now, similarly, for non-independent events, for any set of events, if you're looking at the OR relation, if you're looking at probability of A or probability of B happening. So what is the probability of rain falling or rain not falling? Then it's going to be 1, because it needs to take one of those two choices. But if it's like, what is the probability of rain falling or thunderstorm falling? Then we don't know. Because it could be a situation where rain does not fall at all. So you're trying to measure this individually. So it's given by the probability of rain falling plus thunderstorm falling minus the probability of both happening at the same time. Like a rain with thunderstorm. That will give you the probability for this, as long as you can measure these individual probabilities, obviously. But this is the relationship. These are mathematical laws that are satisfied. Now, the most important, this is the function that we would use for our naive-based technique. So this is a machine learning technique, very popular. Also, it was used very much in spam classification at some point before of emails. So this is looking at conditional relationships. So if A has already happened, then what is the probability of B happening? So if A takes a value of rain falling, so given that rain has already fallen, so there's no uncertainty, no probability you're measuring. I'm telling you, it's 100% that rain is going to fall. The probability that the rain is going to definitely fall, the probability, given that the rain is already definitely going to fall, what is the probability that the cricket match would be cancelled or not cancelled? So it depends on what kind of rain, how long it falls, all that I'm not telling you. So you need to measure that. How do you measure that? This is known as the conditional probability. So you're conditioning, given in a condition, you're trying to measure the probability of another event. So that is given by intersection B by probability of A. This is also known as the Bayes theorem. There's a more, so you can put in a formula for A intersection B in there based on whether A intersection B is independent or not. If it's independent, you put A times B. If not, you put something else. So that's known as the notion of conditional probability. So we're just trying to tell you different kinds of probabilities, right? So you have seen conditional, you have seen probability of one event at a time. Then you can see joint probability, like I drew in in here. So this is also known as joint probability. So you're looking at A1 and A2 happening, or A1 and A2 and so on till AK happening. So you looked at three kinds of probabilities. Standard probability of this kind. You looked at conditional probability formula, what conditional probability means. You looked at what joint probability means. Joint means and. Condition means one is given to known to be happening. It is given that it's going to happen. So what is the probability now that another event would happen based on this situation, right? So if the A was like a probability of earthquake happening, what is the probability that the destruction would be greater than $1 million? Or what is the probability that destruction would be less than $50,000, right? This is B given A, if you're trying to measure. So random variables is just another notation for all these A's and B's. All these random events are also called random variables. So random variable can take different values. So A could be the number of days. So you have two kinds of random variables, right? Discrete and continuous. So X could itself be the event of whether it rains or not, right? So X is a random variable which can take two events. So two discrete events. It's a discrete random variable. Now, X could have as well been a continuous random variable where you have a probability density function defined for whatever numeric number between negative infinity and infinity. Any number you give me, I can give you the probability, right? Then it's a continuous random variable. It is defined not only on rain or not rain. It's defined on a lot of things. So what is the probability? So an example would be, so he gave a preparation example here, right? Amount of preparation time for the SAT, right, is a continuous phenomena. But then what is the probability of getting a score of 300 or 1600 given the amount of preparation time? So this is a continuous phenomena. So this is what you're measuring, but you want to know the probability based on that. So if the student has studied for just 1 hour in his entire life cycle of preparation for the exam, what is the probability that he will get a score of 1600 or 2000, whatever your number is, right? So I want to figure that out based on this time. Now, time is a continuous phenomenon. It's not like dice that you can only take 6 numbers per time. You can take whatever number you want, right? As long as it's a number. So that's a continuous random variable. All right. So now probability distributions, I just drew that on that cartoon which I drew before, right? It's a function of a random variable that gives you, given the value of that function that the event that you're taking, what is the probability for it to occur? So that's the f of x that I was talking about. This is what it is. So if x is taking a particular value, what is the probability of that random variable taking that particular value is what probability density function is. In discrete cases, they call it the mass function. It's just terminology. The same concept in continuous cases is called the density function. And these are the properties. Probability is always less than or equal to 1 and above 0 or equal to 0. And the sum of all probabilities that are possible should be equal to 1. Because if this is all the possibilities that can ever happen in that universe of events, everything should sum up to 1, right? You cannot go beyond that. So this is the two properties. Any function that satisfies these two known as the density function. Right? So there's an example for a discrete case, the mass function. So suppose the random variable x is the number of rooms in a randomly chosen owner-occupied housing unit in a place called Anaheim, California, right? So what is the probability that the number of rooms in a randomly chosen housing unit will be, right? Are there more 3-bedrooms or more 1-bedrooms, or are there more 7-bedrooms, right? It's interesting. So this is just an example of the probability mass function. In this particular case, they gave, say, if you're having 7 bedrooms, the probability is only 0.19. But if you're having a 3-bedroom, probability is 0.76. But a 2-bedroom probability is 0.083. So they're even lesser. So it's interesting that the maximum probability, if you see, happens in here. So it seems to be a very rich place, right? Everyone's having 6 rooms, right? So it's 0.224. At least he didn't say number of bedrooms. So it seems reasonable, like you're adding kitchen and everything. This is where you have the highest probability based on the number of rooms you're choosing. And these preset, you're only taking between 1 and 7. You're not taking 6.5 rooms. Then it would have been a continuous case. And it does not fit the situation because it's not a continuous phenomena. The phenomena is discrete. Now, parameters with statistics, right? So we need to go towards statistics from probability very quickly. So statistics is basically, there is some phenomena that you're measuring, and there are some unknown parameters in that phenomena. If you want to estimate that parameter by looking at the data set, so you look at your sample data and you want to estimate the parameter. That's when you use statistics. So that's what I wrote here, right? A parameter is a number that describes the population. Usually its value is unknown. So it describes the phenomena of the population. So a statistic is a number that can be computed from sample data. So here, if you want to know what is the average what is the room that you would see on average, right? The most. If you counted the rooms in every house in Anaheim, California, you want to see what is the average number of rooms you would find. Would it be 4 or 5, or would you have 7 rooms in general on average? So that is, for example, the parameter you're trying to estimate. The average could be a parameter. Now it's an unknown thing. All you can do is you can sample maybe 1,000 rooms or 1,000,000 rooms, but maybe there are a trillion houses in Anaheim. You don't know how many houses there are, right? So you only sample a smaller subsample of houses, and based on that data set, you can compute the probabilities. But you're trying to, based on those probabilities and based on what you've seen for each number and how much probability you got within your sample, you are trying to estimate what is the average number of rooms. It may be close to your average if your sample is big enough and if your process was correct in terms of sampling. If you only sample from one pocket of Anaheim, then maybe your probability is skewed, or maybe your answer is very away from the truth. Maybe it's correct, right? So all those things go into it. So the statistic is a number that can be computed from the sample data without making use of any unknown parameters. So you don't know the truth, but you want to estimate it. So if you had some good formula and a procedure, then you can call it a statistic. Your sample data is just the data you're collecting. You cannot collect every data point. That's why you're using a sample data. So in practice, we use this statistic that you have come up with to estimate an unknown parameter. For example, it could be the average, or it could be other things if it was a more complicated model that you're trying to go through. So it's the same answer. Here we're talking about the same example about how to estimate mean X bar. So there is a true mean we're calling, say, mu. We can call it the population mean. This is the true average. If you literally wrote down every house and how many rooms there are there in that house, and if you take the true average, then this will be the true answer for the question. But if you don't have resources to do that, you only can estimate it. So if you had a formula to estimate it, and you want to see how close your estimated sample mean is close to the true mean, right? So your formula to estimate this is known as a statistic. The mean itself is known as the parameter you're trying to estimate. This is the true parameter. It's called the population mean. What you come up with from a sample is a sample mean. So that's the distinction between what parameters and statistics mean. So expected value is the formula for computing the population mean. If you knew everything, at every data point, if you knew the probability, then this is the formula for computing the average. So if I knew the probability of getting 1 on a dice is 1 by 6 because the dice is even, because you have 6 possible numbers and each number has a probability of 1 by 6. Calculate if I roll the dice 1,000 times or 1,000,000 times or forever, what number, if I took the average of all the numbers I'm getting, what would that average be, right? That's what you're trying to estimate. So the formula for that is this weighted sum. So it's like a weighted sum, and the weight, I mean, is weighted by the probability of that event times what you're observing. So let me go through this in a little more detail. So in the dice example, what are the R possibilities you can get? What is R? R is 6. So what are the 6 possible numbers xi can take? Xi could be 1, xi could be 2, xi could so on be till 6. What is the probability of the dice taking xi equal to 1? Because it's a fair dice, it's 1 by 6. So what you do is you put 1 times 1 by 6 plus 2 times probability of 2 occurring on the dice is 2 by 6, 3 times 3 by 6. If you compute that number until 6 times 1 by 6 and sum all those things, you would literally get the true answer. And then I can bet if you do this, rolling the dice and writing down on an Excel sheet, if you do that forever all your life and then keep computing the average, it will exactly converge to using this formula. So instead of rolling it 1,000,000 times, just by knowing that you can take only 6 possibilities. Assume this was the dice thing. You can have only 6. If you can only write down this table, you can compute that instead of doing it 1,000,000 times or forever in your life, right? You can compute the average that you would get using that formula. It will converge there. And that will always converge to the true answer. So all you need to write down is write down 6 numbers because there's the 6 possibilities for the dice and write down the probability for each number occurring. In your dice example, it'd be 1 by 6 everywhere. 1 times 1 by 6 plus 2 times 1 by 6 and so on until 6 times 1 by 6, and you add them up. You'll get the true answer of what would be your average number if you had rolled the dice forever. So that's a great example for a good statistic, right? You're getting the exact estimation of your population mean from this formula, which is the sample mean. So that's also known as expected value in statistics. This just means mean or average in general. Similarly, you can measure the variance, right, which is the variability of your data, right? So if I'm measuring the heights of students in a class, if they're varying a lot from, I don't know, for weird reason, from 3 feet to 10 feet, there's a high variance. But in reality, maybe it's varying between 4 feet to 6 feet. But if there was a class where all students were very tall and the variation of the height between 5'7" and 6, or 5'7" and 6'3", then that's a smaller variation. So that's what the concept of variation is, and that can also be estimated. So this is the population variance, is the true variance, but you cannot sample X forever, right? So if you want to estimate the true variance reasonably with this easier formula, which is a statistic, you can use this formula, which is you measure the sample mean, because you don't know the true mean, you take the sample average, and then you see the deviation of each data point from your sample average. So the deviation of each student's height from the average height. You square that up, you weight that up with the probability of that particular student's being so and so. And if you do that weighted sum, you would get an estimate for there's a statistic for estimating the true population variance. So this is a formula that you can measure easily to estimate the true answer without having infinite data from a smaller sample. Of course, if you measure this with only a sample of 3 students from a class of 70 students, then your estimate of your statistics is very away from the true result of what the true variation of the 100 students is. But if you took a reasonable sample, so out of 100 students, if you took a sample of maybe 70 students, then maybe it's good enough estimate of the true variance, right? And also it depends on how you are sampling. If you took the samples only from the first few benches and left the last benches, maybe there is a bias in your variation. Maybe the shorter people are sitting in the first few benches, and then the longer people or the taller people are sitting behind, right? So you need to have a good sampling scheme to use the statistic correctly as well. You cannot just say, I have a statistic, this is the formula to estimate everything correctly.
So here Pune, the first case is xi minus mu, good. But
Yes.
in second case, why xi square? I missed something.
Oh, okay. No, they just opened this up. So they just did some algebra, right? So they did x squared plus mu square, and then minus 2xi mu I. And then what they did is they did the xi square times probability of x, and then they did plus mu I square, and then you have the negative 2xi mu. So here what he did is actually skipped a term, so there's going to be more terms in here. So there's just an opening up here. So this term needs to be corrected. So this is the right formula. But you could also have different variations of the variance formula just by shuffling the terms around. So I can write it down the other way around, which is what was attempted here, but is not done correctly. So the standard deviation is again a common term or formula, which is basically the square root of the variance. So it's measuring the same concept. How is the measure away from the center, which is the mean, right? How is the variability? Any other questions? Okay.
So you said standard deviation is square root of variance or variance square? Okay, variance, right?
Square root of variance. So basically the notation for variance here, which is used commonly in the notation itself, they put sigma square first. So sigma is standard deviation. So the square is the variance. Yeah. It's always the square root. Standard deviation is always the square root of the variance. All right. So for the room example, this is a quick puzzle. You can work through it. Since I gave you the formulas for the expectation variance, you can think about it to measure the probability that a unit has at least 5 rooms, and how you can measure. So there are 3 questions, right? How do you compute expectation, variance, and probability that a unit has at least 5 rooms? So how do you compute that a probability has at least 5 rooms? So by at least, it means it can be 5, it can be 4, it can be 3, it can be 2, it can be 1. So this is your data set for that problem. It's a simple puzzle, a simple exercise. So you just have to sum these probabilities. So if it was a continuous phenomena, all you would do is you would integrate from 1 to 5 the probability density function. But since here it's a discrete phenomena, there is no integral required. Integration is literally a summation, right? So here you would do summation of the probabilities from here to here. So if you sum these up, you get the answer for that. If you summed everything, it will be equal to 1. So similarly for expectation variance, you can use that formula and compute it. Okay, so binomial distribution. Okay, now there are different kinds of distribution functions. So if you remember, distribution function is, it takes in an event, it gives a probability out. The event could be discrete or it could be continuous, right? So there are different kinds of famous distribution functions apart from what is usually observed in the data. So binomial distribution is one such famous distribution. So your possible outcomes is a success or a fail. So it's a discrete distribution, your possible outcome. There's only two kinds that you're trying to measure, and you want to know the probability of success, and then the probability of failure will be the probability of 1 minus success. So this is a notation commonly used. For the probability of success for that distribution, they use P to denote it. So the probability of failure could be Q, which is 1 minus P. There would be a different number of trials that you would, by trials you mean the number of samples you can generate. Now, there is the notion of parameter, statistics, and distribution, right? So binomial distribution has a parameter, P, for example. Based on the choice of P, based on what the probability of success of an event is, you would have a different binomial distribution. So a binomial distribution with P equal to 1 means always success probability is 100%. Whereas a binomial distribution with success probability P equal to 0.2 or P equal to 0.7. So these are different distributions. It's a binomial distribution with a different parameter. So there are different distributions based on the choice of parameter. Now, if I give you a data set of n trials or n samples, so then you will see S's and F's, right? So the success and failures. So if I gave you 5 successes and 3,000 failures in my data set of sample size 3,005, then if you're trying to estimate the probability of success, maybe the probability of success is very low from what you observed, right? Because you observed 3,000 failures and only 5 successes. So then you can estimate from the data what that parameter would have been. Now to estimate that, you can come up with different formulas, maybe just the average you can use, or you can use something else. So your formula for estimating that P for this distribution based on the data of success and failures you have looked is known as a statistic. What formula you use would be the statistic. You could have used the expectation as a formula, for example, because maybe you can assume on average, if the success is, the probability of success is very low, then that could be an estimate for the true probability of success for the distribution from which this data is being generated. So this is the formula for the probability density function for binomial. So this is n choose x, right? NCX, p power x times q, which is 1 minus p power n minus x. This is a given formula. Now, if you literally to do a summation of all possibilities in this, all these probabilities will sum to 1. So if x can take n values, you take summation of all. You can choose 1, p power 1, q power n minus 1, plus n choose 2, so on. If you compute all those terms n times, if you sum it up, it will be equal to 1, because that's a probability any distribution function. That's a property any distribution function needs to satisfy. Now the expected value, if you literally computed using the formula I gave you, right, which is a summation of this probability times the event itself. So 0 times this probability would be 0, of course, then plus 1 times this function. So NC1, P1, P power 1, Q power n minus 1, plus NC2 times P power 2 times Q power n minus 2 times 2. So if you do x times P of x and sum of all of that, you will get a blunt to completely do the algebra on it. It will end up becoming NP. So that's why we say the expected value with that formula, or in reality, or any binomial distribution is given by NP. Where n is the number of trials and P is the success probability. This is the formula. So for any distribution function, once you know the distribution function, and you know that is a distribution of what random variable, it's a distribution of x taking these values, right? If you know the PDF, you always can compute the expected value and variance. So for binomial, instead of binomial, if I give you some other distribution function, I can still use the expected value and variance formula to compute the expected value and variance of that particular distribution. But you need to know the parameter of that distribution, which is P. Now, if I were saying, I give you data and then I want you to tell me not the expected value and variance, but I want you to estimate what P would have been. So the success failure example, I give you a string of how many success and failures were generated based on trials or any phenomena that I'm measuring. Based on that data, if I'm telling you what do you think the estimate of P would be, then you need to think of some new formula. Instead of expected value and variance, you come up with a new formula that will try to estimate P. Right? We will go through these things in the future. So there's another example. Each child born, just from this book, each child born to a particular set of parents has probability 0.25 of having blood type O. If these parents have 5 children, what is the probability that exactly 2 of them have type? So you're interested in, if you're assuming that having blood type O is the success event and not having it as the failure event, is just for naming convention, then you're interested in 2 successes, right? The probability of x equal to 2 is given by n choose 2, 5 C2 times, again, P power Q, P power x, so p power 2 times q power n minus 2, because they gave you that the success probability is already given to you as 0.25. So the failure probability is 1 minus 0.5. So apparently it ends up to be 0.6, definitely less than half. So that's an example for using binomial. You can keep using the same formulas that I gave you. And again, if you have this at least kind of a question, all you need to do is the summation. So first you got a less than equal to 5 rooms example. Now you have a greater than equal to 2 children having type O blood. So you go from 2 to 5 and you sum those probabilities. Then you get this. Now continuous random variable, same concept. Density function, but your variable that you're measuring is a continuous phenomenon. Is a continuous variable, and then it can, each value of that continuous variable will have some probability, right? So same thing. Probability has to be greater than or equal to 0. Sum of probabilities, sum is given by integration, right? So sum of probabilities, all possible values x can take, it should be 1. If you want to get the probability within an interval, so what is the probability that this particular event, say height or temperature or whatever, is between this range, is given by the integration. Because you want to sum the probabilities always, right? So you sum it, and only within this interval from A to B. So you're computing the area under the curve, like I drew in that cartoon there. Okay, so if you're computing, this is like special cases, same, right? So you're looking at just one point. So obviously the area at one point is 0. And then if you're looking at less than equal to and less than equal to on both sides is the same as this. That's interesting. Okay. So same thing. So in discrete case, you had a summation formula to measure expected value. You had sum of it takes times the probability, right? You had sum of 6 plus 2 times 1 by 6. So you had a sum instead of integral here. Internal stuff is the same, right? In a discrete case for the dice example or the house number of rooms example. But if you had a continuous phenomena you're measuring, which can take any real number, then the summation is replaced by the integral. Because the integral is literally computing the sum. Similarly, for the variance, you have a negative infinity to infinity f of x squared dx. Oh, I see. Okay, so I see what is going on here. So it is definitely not a typo. Known as there is a theorem that makes sure that that happens. So it's not visible directly, but if you look at the decomposition of the variance is what it is called. So the law of total variance. So this is a more complicated phenomena that's happening. What you're observing is this. So let me point you to the right thing here. So this is the definition of variance, right? This is known as the law of total variance. So the second formula that you had asked for, Venkat, is due to this law. So I'm going to point it to you in a second. So there's a derivation to it. So basically the variance, the formula becomes this formula, which is how you get the derivation for this second equation that you have here. Because it is saying that the variance can literally be equal to the expectation of x whole square times the expectation of x square. Square is given by, just like expectation of x is x times f of x dx, you're given by x squared times f of x squared dx. So the f of x is borrowed the other side. So what I will do to you, Venkat, is in the continuous case as well as in the discrete case, I will write this down, the derivation of how you went from here to here. In this case as well in the discrete case, and give it to you and send it over the paper. It is known as the law of total variance. As you know, Wikipedia is not very clear, so I will give you the right source and also write down the derivation and send you. So that was a good question.
Sure. Because
yeah, so it is not straightforward. That I can say. It's not trivial. Just by looking at this, you would not get that. There is a whole lot of steps that go in the middle, so it's worth looking at it. And once you be good, you can see these other properties and how these properties of expectation and variance are applied in deriving from here to here. So
in reality, so overall, when we go with this finding a probability and variance and the standard deviation only to identify the hypothesis of success rate are true or false, or all these formulas?
In binomial distribution, yes, but all phenomena is not about true or false. You have some continuous phenomena. So you want to measure not just success, failure, or true or false kind of thing, but sometimes you can measure what is the probability that in next monsoon or in the next rainy season we would have rain more than 6 inches or rain more than 12 inches or snow, right? So then you're measuring not true or false, you're measuring the probability of a quantity or an interval of what you're trying to measure, right? So it's taking a continuous phenomena. So snow more than 5 inches would mean you need to measure the probability of 5 inches plus probability of 5.0001 and so on. You keep increasing till there's not going to be infinite snow, but you keep checking everything possible. Maybe the max you would get is 20 inches or 10 inches. You measure everything. The sum of that is a continuous phenomenon. So then it is continuous probability, right? So in the end, you're measuring probability. It's not only about success or failure. In some cases, you're measuring the probability of success and failure in a discrete situation. If measuring is continuous, then you're measuring a continuous phenomenon. The probability of a continuous interval of numbers happening. Any other question on that or any more clarification?
I think good now. So just I need to explore more. Maybe you will come with a later the detailed explanation of decomposition, right? So after that,
yes,
I'll go through that. And just I was trying to correlate. In general, in any unit we have a standard deviation and recreations and all the formulas, models, right? Blindly people use it.
Yep.
When we go for this behind the scene calculations.
By the way, I have an answer for this. I was thinking through this while I was looking at it, so I will give you the derivation now. Question though, from mathematical perspective. So let's open it first. So you're going to get x squared times f of x, right, which is this term, plus expectation of x squared times f of x, which is one term, and then you have negative x 2 times x e of x f of x, right? So the thing is, of x is nothing but expectation itself. So that's the reason. So let's write this down. So this should be doable. Have x squared. Well, you have x minus expectation of x. The question is this, right? This is the variance. This is the initial where you started. This is the formula for variance, right? So there's no square here. So when you square this up, you get x squared f of x plus expectation of x squared, so just the whole square, f of x, right? And then you have negative 2 times x of x f of x. Let's look at this. So x times f of x, and you're having summation everywhere, by the way. There's an integral here, right? That was the original formula. So this is equal to this plus this integral, right? Which you do not, I hope you do not disagree, right? This is just x plus b whole square formula. So now what you see here is integral of x times f of x itself is the expectation, right? There's the formula for expectation. So what you have is, in this term, you have negative 2 times expectation of x coming from here, and then this expectation of x, which means expectation of x whole square. Okay, so this term is negative 2 expectation of x whole square, and then you had this integral term, and then you have this term, right? So we can keep going ahead like this and see what is left out, and so that we can decompose the rest. So x squared f of x dx, as we saw before as well, is this term, so we're not bothered about that. That's already in. And then all he has is negative expectation of x whole square. So what's going on is exactly this. So this is negative 2. This is plus expectation of x, because this is the quantity that is exactly equal to expectation of x whole square. Do you know why? Do you know why this is equal to expectation of x whole square? This is
because you combine both here.
No, this is coming directly from the formula, because the formula for expectation is x times f of x, right?
Mm-hmm.
X times f of x, or the summation of x times f of x is the formula for expectation.
Okay.
The expectation of x cubed is integral of x cubed times f of x. It's not going to be x cubed times f of x whole cube.
Mm-hmm.
Right? So it's, the formula is you take this and then multiply it with the probability. So this is negative expectation of x whole square,
Mm-hmm.
because your expectation of this event. Now this is, as you see here, using the same formula here, this is the formula for expectation, to repeat. And you have an integral on it, is going to give you expectation. So we have negative 2 times expectation, which is this. So you have negative expectation of x, 2 expectation of x whole square and plus expectation of x whole square. So this is 2 minus 2 plus 1, right? So this cancels out and this becomes 1, which gives you the exact formula, which is this term minus expectation of x whole square, which is exactly what you have here. This term minus expectation of x whole square. So that's the derivation.
I got it.
Okay. Now the same thing in their first question was in the discrete case will be the exact derivation. All integral will become sigma. That's it.
Mm-hmm.
So this is known as the law of total variance, and it's a nice theorem. So I'm glad you brought this up. So this is actually always encouraged, right? So this is a good example for trying to think through and not agree to everything, right? It's not about argument, it's about a mathematical argument. So you're trying to say, why is this the way it is and why it is not? So why is a very powerful question. That will help your learning. So this is that part. As we keep going, I think I will wrap this up quickly. We can cover the rest. We're almost towards the end. So this is another example again. The same thing we've been going over again and again. If you want to measure the probability between interval, you do the integral. So this is a formula for another distribution. I showed you binomial for a discrete. This is a formula for a continuous distribution where x can take any real number. So this is the probability density function. Again, it will have its own mu and variance. You can always compute it using the formulas I gave you. So these are the things we already covered. So just a quick overview. So it's just, we covered this. This is the standard probability. This is the conditional. We covered the concept of joint. We covered the relationship of independence and everything. So in independence, you get this products. So this is the Bayes rule. This will help your homework now. Here in the last couple slides. So if you want to measure, the Bayes rule states that if you want to measure the conditional probability of C given an event X occurs, this is a Bayes rule. It's a theorem. It's just equal to the conditional probability of, you flip this around, of X given C occurs times the probability of C by X. Now, there is a whole book or area of statistics called Bayesian statistics, and the naive Bayes technique is one of the applications of this Bayes rule. So if you want to classify an email as, so if you want to compute the, if say C was the event of the class of email, whether spam or no spam, and X is the properties of the data of the email, the text of the email, you want to compute this, right? You want to compute what is the probability that this particular email given this data set in X is having a probability of class equal to spam or probability of it equal to no spam. You want to measure those two, and whichever is greater will be your answer for your classification. So literally, given this data set, all you need to compute is the other way around. And if you substitute these things, you can compute these using the formulas I gave you. You will get the probability of whether any given email is spam or no spam. That will be your naive Bayes classifier. This is what this is. So D is your data set, C is the class you're trying to compute the probability for. So let me give you a nice example, right? If you're looking at just, if there's a computer vision algorithm you're developing that uses naive Bayes to classify with the gender of any image that you give the algorithm, right? So the computer looks at the images of the people and it wants to say whether correctly classify that this is male and this is female. So your class is male or female, just like spam or no spam in email, right? So, and given the name and instead of image, let's make it easier, right? If you're only looking at the name to start with. So there's Alex Rodriguez, who's male, Alex Daddario, who's female, right? So what you do is you want to know the probability of male given the first name is Alex. Only give you the first name. And if your data set was only 2 samples, instead of like in real life, you have thousands of samples, right? So for a simpler cartoon, this will extend to 1,000 samples as well. When I compare the male given Alex being the first name, the formula for Bayes theorem is this, right? You flip it around. Whatever I gave you the formula, this is the formula. It's a theorem. You can prove this again. Again, you'll have like a set of steps. like the law of total variance. You want to get the true proof of it. But the application of the Bayes theorem is the Bayes classifier. So you compute this. So how do you compute probability of Alex given male? Given male, there is only probability is 1 because you know that if it is male, there's only one person probability that it is Alex. But if you had many other names like John and everything, then you would compute how many out of males had the name Alex. Then that proportion would go here times the probability of being male. If there was no gender imbalance, then we can take it as 0.5. Probability of Alex being the first name in this data set is again 1 because both points in your data set only have Alex. But if you had more data points, you can always compute this in the same way. So like this. So if you had this data set, now let's see. Probability of male given Alex and female given Alex is what your algorithm needs to compute, and then it will take which one has the greater probability as the answer of the naive Bayes classifier. So how do you compute this? Male given Alex, the first term you need to have is the flipped one, right? Which is Alex given male. So from this data set, what is the probability of Alex given male? Anyone wants to try? So I will go over this. I mean, you'll have a sample data set for your assignment. There you can try by yourself as well, right? So just to make sure I'm giving you the right explanation first so that your learning is on the right track. So if you want to compute male given Alex, the first term you want to compute is Alex given male. So if male, the probability of Alex given male, so you want to see how many gender sex is already male. So you have 1, 2, 3 male.
Yeah, 1 by 3.
Yes.
Out of 3, 1. Mm-hmm.
Yes. Out of 3, you want to compute the Alex given male. So 1, 2, 3. In this particular, it is again 3, right?
Correct.
Yeah. So, and then if you want to compute the probability of Alex and then probability of male. So the probability of Alex would be 1 by 8. No, sorry, 3 by 8. 1, 2, 3. So you have 3 by 8. The probability of male would again be 3 by 8 because you have 3 males out of 8. So you compute these for both. And then the 1 by 3 is not coming from this data set. This is a crude example. It's coming from like the like a generic point, like from this line. But what you want to do correctly is this. You're going to compute Alex given male as follows. So if it is given that it is male, then you have 3 possibilities. And out of those 3 possibilities, you have 1, 2, 3 out of 8. Well, you have 1, because you have how many males? Alex is 1 male, Adam is another male, Greg is another male, right? So now this is the right answer. So it's not 8, so it's going to be, let's make it clear. So the sex is male is going to be 1, 2, 3. And out of that, how many Alexes do you have? 1 Alex. And then how many males do you have? 3, because Alex male, Adam male, and Greg male. So that's why you get this term as 1 by 3. Alex given male is 1 by 3. There are 3 people that are male, but only 1 out of those 3 is Alex. So you have 1 by 3 that way. So that's the right computation. So you can do this carefully by looking at this table, or you can even make this into a piece of code that will compute it given a table of this kind to do this formula. And then you compute the same for female, and then you see which is greater. So the greater one would be the answer. So it happens to be the female part of the computation is answer. So you're saying given an Alex, the chance for female is higher. So that's the answer of the classifier. Now, what if you had more than one attribute? Instead of just name, if you're looking at many different attributes, there is a very strong assumption that naive Bayes makes. It assumes that the probability of one variable is independent of the probability of another variable. It's a very strong assumption. It's a bad assumption in most real situations, but that's an assumption that naive Bayes goes by. That's why the name suggests it's a naive algorithm. So how do you use that, right? So if you want to compute the D given CG, which is the first term, right? The flipped part of your first term, so which is this term. You want to compute this term, right? Because to compute the answer, you want to know this term first, then you can figure out these two. You want to compute these terms. What happens is, since you're assuming that your data is not one variable, you have now 10 variables or n variables, right? So you want to, if you're assuming that each variable is independent of the other variable, it's a very bad assumption, but the technique assumes that. So you get some approximation of your answer. It's not the best answer in your prediction. So then what happens is you just have to, for a given class, so for given the class of, say, male, you want to see how many males have name Alex how many males have a no height of 770 centimeter or yes height of 1 centimeter? How many males have eyes blue versus black? So you compute all of those and you multiply those probabilities. So that's what he's doing here. So Alex given probability of Alex, how many males, if CJ was male, then you want to measure how many males are over 170 times. How many eyes are blue. So all the possibilities you multiply, because the law of independence says that independent events, the conditional probability is equal to the product of their conditional probabilities as well. So that is the naive-Bayes classifier. So here, instead of x given c, you have x1 so on till xn given c that you need to measure to compute in the end the probability of c given x, right? Because c given x is this, is proportional to this times this divided by p of x, that's basic proportional. Because the p of x denominator does not depend on the class. So now this is equal to the probability of joint because you're measuring x as not one variable, like many variables, given c times probability. So you want to compute that, but you're taking, it's very infeasible, very hard to compute this. So that's the reason the naive-Bayes took this kind of very naive assumption that all these variables are going to be independent of each other. So now you can break this down as a product of these independent individual probabilities, because independent joint probability or joint conditional probabilities, the product of individual probability or the product of conditional probabilities. Now you compute each of these individually, right? So if you're interested in class equal to male, then for male you measure what is the probability of x1 taking different values, x2 taking different values. Product those up, and then you apply in the Bayes rule. Then you get the naive-Bayes or multivariate, so multi-column database, multi-column data set. So that ends our course for the first week. So I will send you a naive-Bayes assignment, a small assignment that will not have this bigger data set, maybe like some.
So, Pranit, are you sending the slides also? Just I want to follow up.
Yes, we send the slides, we send the video, we also, I will do the assignment as well for computing.
Good. Because I want to go through this video one more time or even a couple of times, definitely.
Yes, you can do.
To understand the last portion, okay?
Yeah.
Bayes and naive-Bayes classification with multi-factor.
Yes, definitely.
I need to. Okay, then I will come with some questions.
Yeah, you can come with questions as well. And then I will also send you an assignment that you can apply to do your learnings.
Sure.
You get a smaller data set, because this thing it's going to take a lot of time. Simply this side. And then other to do, one thing to do other than assignment is for you guys to identify some data set from some links that I've sent. So you will get a summary email from me about the assignment and these resources for identifying data sets for projects. So then we can catch up with the next week after that. So it's a good time to end the call. Any other questions, concerns?
Pranit, can you tell like what's the difference between the Bayes and naive-Bayes? Is there any difference?
Bayes rule. So Bayes was the name of the scientist, right? So Bayes rule is the theorem where you have conditional probability of c given x is equal to x given c times p of c plus p of x. So that's the Bayes theorem. Naive-Bayes is the name of the technique for the classification. So naive-Bayes is a technique using the Bayes theorem.
Okay, so Bayes theorem is it a simple version of naive-Bayes? That's what can I understand?
The other way around. The naive-Bayes is a simpler version of Bayes theorem, because in Bayes theorem you have this conditional probability as one of the terms in the numerator. The conditional probability is very easy to compute if your variables are assumed to be independent, because you only compute them individually. So that the Bayes theorem with the independence assumption between variables is naive-Bayes. So naive-Bayes is exactly the Bayes theorem with an independence assumption for probability.
Okay. Okay. Yeah, thanks.
Cool. Any other questions?
Yeah, thank you.
All right. So you have a good one. I will reach out to you in an email summary.
Okay, bye.
Thank you. Bye.